Hello students, welcome to the online video lecture of Computer Organization and Architecture course. Today's topic for discussion is Booth multiplication scheme. In the last session, we already discussed sign extension multiplication mechanism. So let us go for Booth multiplication scheme. Under this topic, we are going to discuss two examples. Let us go for the examples. In the very first example, I have taken multiplicand as minus 13 and multiplier as 11. There are three simple steps of Booth multiplication. Let us discuss one by one. In the step 1, you have to append 0 to the right of least significant bit of multiplier. In our example, the multiplier is 11. Binary representation of multiplier is 1011. I have represented 11 by using 5 bits. So extra 1 bit is added. So after appending 1 bit to the right of the left significant bit, the multiplier is of now 6 bit. Very simple. Let us go for the next step. In the second step, you have to create recoded multiplier. For that, you have to follow the simple two steps. First, you have to make the pair of 2 bits starting from left significant bit of multiplier. Okay, and in the second step, you have to actually create the recoded multiplier, but with the help of recoding table. Here you can see the recoding table. Okay, so let us try to make the pairs. In our multiplier, you have to start with left significant bit. So this would be the pair 1, this would be the pair 2, the next pair is pair 3, pair 4, and finally you can consider the pair 5. Now you have to create the recoded multiplier with the help of this recoding table. You have to see the bits from right to left. This bit is considered as a I minus 1 bit for understanding purpose, and this bit is considered as a I bit. So in the first pair 0 1, so 0 1, for this I have to take minus 1 as a recoding bit. So I have taken minus 1 here. For subsequent pairs, for 1 1, in the second pair I have to consider 0. So very simple, here I have taken 0 bit. For 1 0 1 0 1 0, here I am taking plus 1, so plus 1 is written here, and subsequently I have finished with all the recoding bits. Now this would be the recoded multiplier. Now let us go for the next step. In the next step, you have to actually do the multiplication, but you have to simply understand one rule. Rule is very simple. So when I multiply minus 1 to the multiplicand, I must have to take 2's complement of multiplicand as a partial product. So here I have already calculated 2's complement of multiplicand. In our case, multiplicand is 1 0 0 1 1. So How to calculate the 2's complement? It is very simple. You have to first take the 1's complement. So 1 is represented as 0, 1 is represented as 0. So 0 is converted as a 1, 1 and 0. You have to simply complement the bits. And you have to add 1 to the left significant bit of 1's complement. So 0 plus 1 is 1. Remaining bits are written as it is. So this is the 2's complement of multiplicand. Now let us go for the multiplication. In the multiplication, multiplicand is minus 13. The binary representation is written here, and here you have to use the recorded multiplier. So the very first bit is minus 1. So whenever I multiply by minus 1, I must have to take the 2's complement of multiplicand, which is already calculated here. So I have directly written this 2's complement, and now the remaining bits are to be taken as a 0 because our product must includes 10 bits because multiplier is of 5 bits. So I have to simply extend this most significant bit 5 times. Okay. Next. So the next multiplier bit is 0. So if you multiply with 0, ultimately the product becomes 0. So I have to write 5 times 0. 1, 2, 3, 4, 5. And remaining bits are again filled with 0 because most significant bit is 0. This is a sign extension, I would say. Next iteration, you have to multiply with plus 1, and if I multiply with plus 1, I have to simply write it down the multiplicand as it is because here 1, 1, 0, 0 and 1, and the remaining 3 bits are again filled with sign extension. So 1 is extended 3 times. And again in the next iteration, the multiplier bit is plus minus 1. Here I have to take the 2's complement form of multiplicand, which is already calculated here. Directly I have written here, and remaining these 2 bits are again extended with sign extension. Okay, and now last iteration multiplier bit is plus 1. Here you have to directly take the multiplicand as it is, and the last bit is again extended with most significant bit. Okay, now we have done it. Simply now addition is to be done. In the first column only single bit is there, so directly I had written 1. 0 plus 0 is again 0. 1 plus 1 is 0, and here the carry generated as a 1. So 1, 1, 1, 1. So 4 times 1 is there. So 4 times 1 means in binary I can write it down 1, 0, 0. So this 0 is to be taken as a sum, and remaining 2 bits are taken as a carry for subsequent columns. Okay, fine. So 0 plus 1 is 1, and now again 1 plus 1 plus 1, it is again 3. So in binary I can write it down 1, 1. So this one is to be taken as a sum, and this one is to be taken as a carry. So here carry generated as a 1. So 1 plus 1 plus 1, again 3 times 1, so 3. So again 1, 1, 1 plus 1 0, carry 1, 1 plus 1 plus 1 3, again carry generated as a 1, 1 plus 1 plus 1 3, and now whatever the carry generated, this carry is now discarded because our product is of only 10 bits. Okay, now let us go for the next example. In the next example, I have considered plus 13 as a multiplicand and minus 6 as a multiplier. So very first step is to append 0 to the right of the left significant bit of multiplier. So the binary representation of uh, -6 is 11010. Here 5 bits are to be taken for the representation, and yes, I have to append the 0. Now it becomes 6 bit. In the next step, I have to create the recoded multiplier. First, I have to make the pair of 2 bits starting from left significant bit, and then by using this Booth multiplier recoding table, I have to create the recoded multiplier. So this would be the pair 1, pair 2, pair 3, pair 4, and pair 5. Look at the table. This would be the my I minus 1th bit, and this would be the ith bit. From right to left, 0 0. I must have to consider 0 as a recorded bit. 0 1, for this 0 1, I have to consider -1 as a recorded bit. From 1 to 0, this pair I have to consider +1, and subsequently I can write it down the remaining pairs. So this would be the recorded multiplier. The next step is to do the actual multiplication. It is again very simple. In the previous example we discussed in detail. Let me do the multiplication. Okay, fine. Okay. So one rule you have to always remember: whenever I multiply by -1, I must have to take the 2's complement of multiplicand as a partial product. So already I have calculated 2's complement of multiplicand. In our example, multiplicand is plus 13. So first I have to take 1's complement. 1's complement is very simple. It is a invert operation. One, if there is a 1 bit, I have to take 0. If there is a 0 bit, I have to take 1. And I have to add 1 to the least significant bit of 1's complement. So after adding, I am getting 2's complement of multiplicand as this particular binary pattern. The next step is to multiply 13 by -6. So very first bit of multiplier is 0. When I multiply by 0, obviously I am getting 5 times 0. And remaining bits are, as we already discussed in the previous example, are extended with 0. Very simple. Next bit is -1. Here I have to consider the 2's complement of multiplicand, which is 1 1 0 0 1, and the remaining bits are again extended with 1. So in this way we can uh, make the addition now. 0 1 1 plus 1 0, and the carry generated as a 1 1 plus 1 0, carry generated as a 1. So 1 plus 1 plus 1, it is 3 times 1. 3 times 1 means in binary I can write it down 1 1. So one single 1 is written here, and next bit is to be taken as a carry. 1 plus 1 plus 1, again 1. 3 times 1. So 1 carry will be generated as a 1. 1 plus 1 0, carry generated as a 1. 1 plus 1 plus 1, carry generated as again 1. 1 plus 1 plus 1, carry generated as again 1. 1 plus 1 plus 1, and the carry generated as a 1, which is to be discarded. So this would be the 2's complement form of -70. You can cross check by converting this particular number -78 into a binary form using 2's complement. Now let us try to discuss the various multipliers. See, we are taking three different codes. three different multipliers, and now we are going to learn the efficiency of Booth's multiplication. So this is a worst case scenario. Here if you observe, we are getting -1 +1 -1 +1 -1 +1. So ultimately, whenever I multiply with -1, I have to add 2's complement of multiplication. So it takes time. So obviously, if I am getting -1 +1 -1 +1, ultimately the efficiency would be is reduced. And in the second case, this is a one kind of ordinary multiplier where I am getting few -1 and +1. So I can say I am getting average efficiency. And in the third case, this is a good multiplier. Why this is a good multiplier? Because if you observe here, we are getting the original multiplier. If you look at here, we are getting sequence of ones. And whenever we are getting sequence of ones, ultimately, if I look at this pair, recorded multiplier bit is 0. If I look at this pair, recorded multiplier bit is 0, and we know that whenever we multiply by 0 bit, ultimately the result would be the 0. So here I can achieve some kind of efficiency. So let us discuss the various features of Booth multiplication scheme. There are two different features. The first one is it can handles both positive as well as negative numbers uniformly. Means Booth multiplication can work for signed operands. It can work for positive as well as negative multipliers, and it can also achieve the efficiency if number of additions required, in terms of number of additions required, if multiplier has large blocks of ones, that we already discussed in the previous slide. I simply give you some exercise task. You can simply go through these two examples, and if you can't understand, then I simply request you to please go and see back, go and see the video again and again. Surely you can understand. Thanks for watching the video.